All right. So what we're gonna kind of talk about, we're now kind of in the interesting kind of portion of, I mean, the whole course is interesting, but I'm biased. But no, I think, the why are we learning all these techniques is because we want to do predictions. We want to kind of say something. We want to actually infer and make predictions. And so now we're going to kind of start that journey. And it's actually, it's something that we've actually looked at very early on in the semester. So we're going to come back to this topic. And so, right, predicting basically means we're going to guess the future, and we don't have complete information to do that. So we're going to make a guess. We're going to make a guess based on incomplete information. And so one way, in the way we've actually looked at earlier in this course, one way of making predictions is, so if we want to predict an outcome for an individual, what can we do? Well, we can, if we don't have complete information on that individual, but what can we do is we can look at similar individuals. We can look at similar individuals where we actually know the outcome. Okay, and we can use those outcomes as a basis of our prediction. And we saw this when we looked at the height, Galton's height data set. And just kind of as a review, what we were doing here is collected a lot of data and about parents and their children and their offspring. And the data that we looked at was, can we use the parents' heights to predict the future height of the child, right? Presumably when the child becomes an adult, and so we settled on this predictor variable, which we called the mid-parent height, and so it was just the average of the height of both parents. Okay, so this is the kind of the variable. So we take the average of the parents' height, and we actually were using that to make a prediction of the child. And so we're not doing that here. We're just looking at a visualization. We're looking at a visualization of that. And you can see, just kind of by looking at the scatter plot, you see that there seems to be something here, right? As the parents, the mid-parent height gets higher, so does the height of the child. And so what did we do to make a prediction of a child that is not in the data set, right? So this is our data set, and so we have another child come along who's not in the data set, so we don't know. Well, and they're still a child, right? And so, how did we go about making a prediction? So what we did was if we were making a prediction about a child whose mid-parent height was 68. So what we did was, we took our data sets and we looked, I think, a half inch either way. So we looked at the neighbors, we looked at all of the neighbors, and we came up with an average. We came up with an average of all of these known observations, and that was our predictor. That was our predictor. And then we ran this through all of the all of the data that we had. And so this gold line here, this was our prediction. This was our prediction from that. And you can see one thing that kind of jumps out is that, so because we're taking the average of these neighbors, even though it's kind of scattered around, these predictions, kind of look like a straight line, right? We've got a little something kind of going on here, but this relationship or these predictions certainly appear to be linear from there. Okay, and so. Like I said, in this case, the predictor variable is our mid-parent height. And so now we've made our predictions. And so one thing that we can do once we've kind of done that, we should evaluate how well did we think we did. And so one way to do that is we can look at prediction errors. And we found actually kind of something very interesting when we actually looked at the prediction errors based on sorted out by the gender of the child. And we see that looking at the darker blue line, we can see that this, our prediction tends to over-predict the height of females and under-predict the height of males. And so what we can do, and then we quickly looked at it. So what happens if we had separate predictors, right? So a smarter prediction actually just didn't look at the midpoint. It still looked at the midpoint, the mid-parent height, but separated it by gender from there. And we can see that we had a much smarter prediction from there. And so this is known because we're taking these averages in here. This is known as a regression prediction. Okay, and so what we're doing for our prediction is it basically lies at the center of the vertical strip, right? So if we take any given prediction, right, let's look at 68 again. It lies roughly in the middle of the vertical strips of points right at 68, okay? And so now what we want to do is we want to look at more formally of whether these variables act as a good predictor, okay? And that leads us to our next topic, association. Okay, so okay, so let's say we have two numerical values, like we did in the Galton data set. One of the things that we can do is, and this is always a good idea whenever we have a new data set, we should just look at the data. We should explore the data. And if we're comparing two numerical values, one thing that we can look at is the trend. So as one variable increases, what is the relationship to the other variable? What is that trend? And we can see one trend could be is that we see a positive association. So as the X variable increases, does the Y value increase as well, right? That would be a positive association. But we could also have a negative association, right? As the X value or just one of our variables, if that increases, if that causes a decrease in the other variable, that's known as a negative association. And so this is the kind of like a positive association if you're kind of plotting X and Y, right? Positive association, it's sloping upwards and to the right. Negative association, it's going to be sloping. It's going to have a negative slope. It's going to slope downwards as it goes to the right. And we can look at a pattern. We can look at the pattern of the data as well. And so what do we mean by pattern? Is there some shape in the scatter plots? One of the easiest patterns and one that we'll focus a good chunk of our attention on is a linear pattern. Do they go up in a line from there? But we can also have, and we'll look at some examples of nonlinear relationships where there is an association. There is an association, but it is not a linear one. And so the kind of general roadmap that we want to follow is let's visualize and get a sense of kind of to get a handle on what the shape of the data looks like. And then we can go on and actually quantify. We can put a number, we can put a summary, statistic, a number to what we visualized. Okay. Please feel free to ask any questions while I'm setting up the demo here. All right, so up there, everyone can see this okay? Please speak up if I need to make it bigger. Good, I got a thumbs up. All right, so one thing we're gonna do, so I'm just gonna write this. We don't actually need to know how it works. What this is gonna do is this is gonna help us kind of understand association. So I'm basically making some plots of different correlations from there. So we don't have to worry about how that works. And so for this data, we're going to look at this data set of hybrid vehicles from there. And so it has the vehicle, the year, and then it has the price, the MSRP, the manufacturer's suggested retail price, the acceleration, so how fast it goes vroom. And I suspect this is probably this is probably the time. This is probably the time to go from 0 to 60 from there, and then miles per gallon of all of these hybrids, and then the class. So we're going to focus on numerical categories. So we're going to focus on the MSRP, acceleration, and miles per gallon, and we're going to just kind of explore and visualize the data to see if we can see any of these associations. Okay, so that's the game plan. So we have our data, and so acceleration. Oh, so that's I stand corrected. This is definitely not like the 0 to 60 times, because the larger the number, the faster the acceleration. So stand corrected on that one. And so first we'll just look at the MS. Let's look at the MSRP. So we're just looking at the histogram of all of the. So we're just looking at the distribution. And you can see there's kind of a big, it's not terribly evenly distributed, right? It looks like it kind of curves and tails off, which kind of makes sense, right? These really expensive, this is a car that, cost over $100,000. And so, but you can see definitely there's kind of a sweet spot, right? Around like 30,000 for all of these cars from there. And then if we sort, we can see that most expensive cars are Lexus from there. And then let's look at now. So now that we're looking at the MSRP, now let's look at two variables together. Let's look at to see if we can see any associations between how much the car costs, the MSRP, and miles per gallon. And so just as kind of just the standard format, the x-axis is typically the predictor value, so the variable. And so then the MSRP is going to be our prediction. And so then the question is, if you had a given miles vehicle, if you knew the miles per gallon, can you predict the cost? But we're not there yet. We're just kind of exploring the data and looking at associations. And you can see there definitely kind of is right. And so, is this a positive association or a negative association? Well, you can see that if there, there's definitely kind of a trend where as the miles per gallon increases, the cost decreases, right? So that's going to be a negative. That's going to be a negative association. And the other thing to kind of note too is that, does this look linear? I mean, parts of it kind of look linear, but it kind of looks like a curve, right? Looks like as the miles per gallon increases, it kind of slopes. It kind of has a little bit of a curve to it. So, but there's definitely some kind of, there's definitely some association here, and it's definitely a negative association, and that seems kind of interesting at first. But, some of the more expensive cars, they typically have higher horsepower, and so they're going to be less fuel efficient. So maybe that explains some of that. But if we look at the acceleration and the MSRP, we definitely now we see a positive association. As the acceleration gets, as the cars have more acceleration, they tend to be more expensive from there. Okay, so we don't have to look at all of it. We can just focus on a class, and if we just look at the SUV class, and we look at the MSRP, and so now this is compared back up here. We see kind of for all the cars, it wasn't terribly evenly distributed across the MSRP, but here it looks a little more even across the board from there. And again, we can look at if we look at the acceleration, we can see now definitely a positive. We can still see a positive correlation. And then if we look at miles per gallon, we can see a negative correlation as well. And this one looks more linear, right? We had up here the one that looked like a kind of a big curve. This was the miles per gallon and MSRP. If we just looked at the SUVs, this looks a little more linear. Okay. So one thing that we want to do when we visualize the data, right? So notice the units. This is in acceleration, and we just kind of have we use the default, so plotted from 8 to 18. This is in miles per gallons, and so it makes it hard. It makes it hard to compare one scatter plot to the other. So the thing that we almost always do is we convert, and we've done this and we've looked at this before. We almost always convert when we do these scatter plots. We almost always convert to standard units. Okay. And so if you remember what converting to standard units are, all we're doing is we're taking our data points and we're seeing how far they are. Each data point is away from the average of all of the data points, divided by the standard deviation of our data points. Okay. And so we're going to do this enough that it makes sense to have a little helper function. And so this is just going to take in any array, any data array, and it's just going to convert to standard units for us. Okay. And so now, and so here's our plot before we converted. And so all we're going to do here is we're going to make a new table now. We're going to take our miles per gallon and our MSRP. We're going to convert that into standard units. Okay. And so the thing I want you to see here is, and so this is the same data, and it doesn't change the relationship between the data. If I can kind of fit everything in here, right? You can see that the shape of the data is exactly the same. Here's all the data points. All we're doing is changing the units. And so we're just either kind of elongating or squishing them together, but it doesn't change the relative shape of the data. The data is all here. But now, now that we've converted to standard units, right, it's going to be centered on it's going to be centered on, so instead of just looking at the, kind of in the middle here is kind of the mean of the data. Now, because we're in standard units, we're talking about a standard deviation. So regardless of the data that we have, the center of the plot is going to be 0, 0 from here, okay? And so now this will help us when we start looking at these associations. It's going to help us compare different graphs from one to another. And so we can do the same thing here. And this is now looking at acceleration in standard units versus the MSRP. Okay. And so you very clearly can kind of see the negative association here for the graph on the top. And you can see the positive association from here. Okay. All right. Any questions kind of about association? All right. Great. Okay, so now that we kind of looked at this data, we can kind of see this association. Let's make this more formal than just kind of looking at things kind of, either are they sloping up or are they sloping down. And to do that, we have this correlation coefficient. And this is known as R, right? So R, if you just refer to it as R, all the statisticians will know exactly what you're talking about. And so the correlation coefficient is, again, this is going to be assuming our data has been converted to standard units, okay? And so what we're going to do is just kind of take a look at the second half, right? So we're going to take the product of our X data, so our X-axis data, and then we're going to take the product of our two data, right? Our X and Y data in standard units. We're going to multiply them together, and then the correlation coefficient is just going to be the average of that product. Okay, so take all of our data. The product of X times the product of Y, do that for all of our data, and then so we'll have the product of all of that, and then take the average of that, and that gives us our correlation coefficient. Okay, and what that means is it is a measure of how clustered our scatter is around a straight line. Okay, and I'm gonna show you pictures of this that will make this very clear. And so because this is a measure of how clustered our data is around a straight line, so this is going to be, it's going to measure the linear association between the two data, between the X and Y, for that data. Again, the correlation coefficient we've converted to standard units, so it's going to be based on standard units, and R will always fall within the range of -1 to +1. It will always fall in that range. And so if we have kind of, look on the one extreme, R is 1, that means we have a perfect correlation between X and Y, and it's a straight line sloping up. Okay, and I'll show you pictures of that. So when R is positive, that means we have a positive association. The line is going up and to the right. If R is negative, and again, with -1 means perfect correlation. Negative means it's going to be sloping down as it goes towards the right. And then kind of the exact middle point, if we have R of 0, we say that there is no linear association. That means that data is uncorrelated, okay? It doesn't mean that there isn't a relationship. It just means that there is no linear association with that, okay? And so let's take a look at that. Let me just reload this. Okay, that's just our scatter plot from here. So here, so how do we calculate R? And so what I'm going to do up here is I'm just going to make some phony data, some made up data. And so I'm just going to have a table here, small table with 6 items in it. And so here is our X and Y data. And so here I'm just going to show you this, just take a look at the scatter plots of that. And you can see the data here. And so remember, the first thing that we want to do is we want to cover, because this is in our regular data units, whatever that is, but we want to convert to standard units, which is basically unitless from there. So we can just run the same standard units function and then run that on our data. So then we're going to have X in standard units and Y in standard units. And then we can put our data, fold that data back in. So here's our table, our original table X and Y, and here we've just added the columns in standard units. And then again, the point I want to show you. So now we're plotting in standard units, right? So since we're plotting in standard units, the data itself, the relationship between the data doesn't change. It's just the units that we're presenting our data in from there. Okay, so to get the correlation coefficient, we convert to standard units, and then we're going to take the product of that array. And we're going to take the average of that product. Okay, so here we've calculated the product. And so now we can add it for all of our data points. So here we have the product for each of our X and Y pairs. And then finally, to calculate R, we're just going to take this column, the product of the standard units. We're just taking the average of that. We're going to take the average of that. And then we get this measure, this 0.61. And if you remember R is going to fall between +1 and -1. And when we have, when R is positive, that means the association is positive, which means in general, as X gets larger, Y gets larger. And we see this kind of for the most part. We certainly see this for this data here, but we have a couple of points there. But in general, as X gets larger, so does Y. We have a positive association. from there. Okay, so we can just basically wrap up all of those calculations that we've done in a helper function. And so what this helper function here, what this does is that this takes a table and it takes two column labels, X and Y, and then it's going to return you the correlation from that. And so all it's doing is first converting those columns to standard units, taking the product, and then taking the average of that. Okay, so now we can, instead of doing all of those calculations by hand, we can just call our helper function. And you can see when we passed in our table T with X and Y, we got the same answer that we did doing it by hand. So now that we have that, we can actually look at the data that we looked at before, but now get a measure of how correlated the data is. Okay, so this is just the same table here. We're just looking at the SUVs. And then now we can see what the correlation is between the miles per gallon and MSRP. And we saw last time, as the mile per gallon was going up, the cost was going down. So we have negative association and conversely a negative correlation of minus 0.66. And again, if we look at the scatter plot from that, we can kind of see that. We can see that association. If we look at the acceleration, we see it's not as strong a correlation, right? Because the magnitude tells us the strength of how clustered they are on a straight line. And here we see a positive correlation, and it's not as strong. It's a little more scattered than this one here. Okay. And so now we can use this. We can use this scatter plot that generates synthetic data that corresponds to a particular R value, and we can see what this means. So -1 is the extreme. That is perfect negative correlation. And what does that look like? That looks like, as our data again converted to standard units, it all falls on this line, right? And so if we had a value of 2, we would predict that we would get -2. If we had a value of 3, we would predict -3. If we had a value of -2, we would predict 2, right? So there's this negative association in this perfect, all of the data is clustered on this line, on this line with a slope of -1 here. And so if we kind of back off that a little bit and see what does it look like when the correlation is 0.9? Well, we're going to see definitely a pretty strong data, but it's fuzzier, technical term. It's fuzzier around this line, right? So it's not as tightly controlled, but we definitely see that line here. And then if we kind of back off a little bit, we can see as the scatter, as the correlation goes to 0, our data becomes fuzzier and more blobbier, right? It is just getting more kind of clustered. It looks more, instead of a line, it looks more like a circle. And so if we take a look at that, again, a 0.5, right? So there's definitely an association here, but it's certainly less strong, less predictive value from here. And then we can also see too, right? So we've looked at all of the negative ones for sloping down. This works exactly the same way for positive correlations as well. And again, if you looked at 0.1, you can see that the line is tightly directly pointing up in that direction. And then it's worth looking at, what does a scatter plot of 0 look like, where there's no linear correlation, right? It looks like just a kind of a blob centered around 0 from there. Okay. If we calculate the correlation and change up the axes, because we're computing the average of the product, switching the axis is going to have no change on the correlation. And this makes sense, right? Because we're taking the average of a product. X times Y is going to be the equivalent to Y times X. And so if we take the correlation of X and Y, we're going to get the exact same correlation that we did for Y and X. Right, 0.61, 0.61 from there. Okay. Any questions about that? Right. Okay. So now, wrong button, wrong button. All right, so now that we have this way of quantifying, are there some limitations to this number, right? Always when you put a number on it, let's remember kind of what that number represents, what that model is, and when does that model break down. So here's the general things to watch out for, the general caveats when dealing with R. One is that remember what this is saying, right? This is saying, is there a linear relationship between the two data, between our X and Y data? And so we're saying a very specific thing, that there is a linear relationship. If we get R of 0, all we're saying is that there's no linear relationship. There could very well be some other type of relationship, but it's just not a linear one. Outliers can take what could be perfectly linear association, and that can throw that off. And then there's this idea of ecological correlations, and I'll show you an example of this in the demo. And basically, kind of what it means is that when you're starting to look at, you should look at kind of where that data is coming from, and you don't want to overgeneralize what that says about a population. And so let me show you again some of the pitfalls or some of the things to watch out for in demo form. Okay, and so nonlinearity. Okay, so here we're going to generate some data. And so if you look at this data, you can see that there is definitely an association, right? And so you can see how I generated the data. X is related to Y. Y is going to be the square of X. So there is absolutely a relationship between X and Y. But if we take this data and we run our correlation on it, we get a correlation of 0. We get a correlation of 0, right? So what this is saying is that there is no linear correlation between X and Y. But there very clearly is a nonlinear relationship between the data sets. So like why you just got to keep your eye out for that. And usually, right, we kind of recommend always starting off by visualizing the data and taking a look at it, right? It would be very clear if you kind of visualize the data that everything that you would see that there's definitely some relationship, and it's very clearly non-linear. So if we look at outliers, and so here again, this is kind of artificial data, so you can without even doing the calculation, we can see that this correlation is going to be 1 from here, right? Is for whatever the input is, the output is the same. But let's look at that data again with an outlier. Okay, so you can see that here's the data. The only thing I changed was this last data point here from there. How do you think that's going to affect the correlation? In this case, it has a very drastic effect, right? It's saying with this data point from here, we're saying that there's actually no correlation. And is that true or not? It's tough to say. It's tough to say. Is this truly an outlier? Was someone, was the equipment failed when it gave this data point? Did someone type something wrong? Was there just, some other explanation for that? And of course, with 5 data points, that's actually pretty hard to tell from there. But, outliers can have an effect. Here's an example of an outlier, another outlier, but this one isn't quite as a drastic a change. But you can see it has definitely affected the correlation. And so the last thing I kind of want to kind of bring to your attention is these ecological correlations. And so here what we're looking at is we're looking at the statewide SAT scores. So this is going to be, if we look at this, so this is the SAT scores for all of the students for all of the state of Alabama and all of the other associated states from there. Okay. And so we have some numerical columns, so we can naturally compare them. And if we can compare their scores on the critical reading portion of the exam to the math portion of the exam, you can see a very, very high correlation, extremely high, right? If we calculate this, we can see that it is actually 0.98. So what that means is if you did well in critical reading, you did well. The prediction that you do well in math, right? And that is kind of borne out. But even though there's such a high correlation, I want you to think about what this population data is. All right, this is not an individual student, right? This is taking the average of all students across an entire state of Alabama. And so, I caution you to make, kind of strong statements that, well, the best way to get a good score on math is to learn critical reading, right? Because we're really looking at a very, very broad, we're looking at an average across a very, very large population. And so if you actually looked at individual students, you're going to see a much larger variation in these scores. Okay, so that's something to be kind of aware of. Especially, I want you to think about this when you think about when you're doing your projects as well, and especially if you're looking at big summary data from there. Okay, so that's just something to kind of keep in mind. Okay, so all right, I think we have enough time to do a couple of discussions, and then we'll be able to wrap up for today. Okay, and so for this group, basically, I won't send you into breakout groups, but let's just kind of think about each one of these and just talk about them for a moment. Okay, so for each pair, so I'm showing you two scatter plots again, but all of them in standard units. So for which pair, which one will have a higher value of R? Okay, and so let me be specific. So I'm asking for this. Just look at the, we know when R is positive, it's when R is positive, it's going to be a positive correlation. When R is negative, we're going to have a negative correlation. Just to reduce some ambiguity, what I'll talk about when I mean by higher value, I mean just the magnitude of R. Okay, so which one do you think will have the higher magnitude for A? So let's just look at A. What do you think? Which one has the higher R value? Which data set looks more correlated? Does anyone want to, you can say in the chat, or someone can speak up. The right-hand one. Yeah, right? It is definitely looking a lot more clustered around a line than the one on the left. Okay. How about B? Left. We got lots of lefts. Yeah, right. And then this one, it's pretty clear between there. But C now? How about C? Which one do you think will have the higher R value? And let me be clear, in B, right, both of them will be negative. Both of them will be negative, and negative association because the slope is pointing down as it goes to the right. But the magnitude of B is going to be larger than the magnitude, the one on the left from the right. Now, what about C? Okay. All right. So see, this is now we're getting some we're getting some both. And I think this one is definitely, out of all the ones we've looked at so far, the most ambiguous from there. I think the thing that, so I would go with the left one in this case. And the thing that kind of tips it in that favor is that they roughly look kind of the same, the main blob, but the right one has these outliers here, which I think are going to kind of drag down the correlation coefficient from there. Okay. And then what about the last one here? This one's tough. What do people think? Yeah, so I'm getting some lefts, I'm getting some rights. And this one's close. This one is close. I think just looking at this one visually, I think it would be, I would think it's too close to call. If I had to guess, I would probably say the left one, but I think you can make an argument for the right one. The reason why I would say the left is I'm really concerned about these outliers here. I'm out of on the either side there. They seem to be kind of equally balanced on either side, which I think is going to draw this, closer to zero on there. But this one, I don't think you could actually make kind of a judgment call on this one. I think you would actually have to compute the correlation coefficients on that to do that. Okay, and so, all right, let's just wrap up with this this discussion question here. They're just a couple of true and falses, and then we can head out. If X and Y have a correlation of 1, then one must cause the other. True or false? I see some falses. Yeah, so this is false, right? And so again, right, this correlation is this measure of association. We have not said anything about causality. We haven't done any experiments on the data. All we're saying at this point is that there is an association. We've not said anything about causation from there. And as we saw, right, we can actually change the axes, and it doesn't actually change the correlation. Okay, if correlation of X and Y is close to 0, then knowing one will never help us predict the other. True or false? Okay, I see some trues. I see some falses. So this one's a little more kind of ambiguous. So and this comes down to so I would go with false on this one. And the reason why I would go with false is because remember, the correlation is just a measure of a linear association. There could be an association that's not linear. And so if that was the case, and we looked at that example of the y equals x squared, right? That had a correlation of 0, but if we knew the model, and we knew that it was an x squared relationship, well, the knowing one will be very predictive of the other. So I don't think we can say that, we can't say that in all cases. We can say that if there's a linear relationship, it wouldn't be. And then finally, if X and Y have a correlation of -8, then they have a negative association. True or false? True. Exactly, right? And that comes straight from the definition. All right, sorry I kept you over a couple of minutes. Let's wrap up here. This is a perfect place to wrap up.
Okay. Okay, so I think last week Jason went through most of topic 24, prediction and correction. Okay, but he told me that there are 2 additional slides that will be good to discuss before we move to the new topic. So I'm gonna start with that. And this is, if you remember what we had done before, like I think it's topic 7, which we're gonna revisit in a second as well, is how we're thinking about prediction back then. Okay, so to refresh your memory a little bit, we did what we call a nearest neighbor prediction. Okay, so what happened before is with the Galton data, if you remember, we have the parent's height. Okay, we have, so the father's height, the mother's height, and then also in the data, we also have the child's height. And to predict, okay, so you might be interested in predicting the child's height given the parent's height. Okay, so what we did is I think we took the average, right, between, so for each prediction, what we did is we find the average of the father's height and the mother's height on what we call as mid-parent. Okay, we get that parent height, like mid-parent height. Okay, and then what we did is that for a particular mid-parent height, like 68, for example, if you remember, we looked at all of the children's height within 68 minus 0.5 and 68 plus 0.5. Okay, so essentially what we did is that we collected all of the children's height when their mid-parent height are within a small range, okay? And then we took the average of all of the child's height as a prediction for somebody whose mid-parent height is 68. Okay, so that's what we did before. Okay, we called it regression, and then later on in next topic we're going to specifically talk about like what we call like linear regression. So they're related to some degree, and we think this is a good chance to review what we did before, and then just to refresh your memory about how we did through Python as well. Okay, we wrote a function and then did that prediction. All right, so to recap what I just said, pretty much we group each x, okay, the predictor with similar nearby x values, okay? We're gonna average, okay, the corresponding y values for each group. So in that Galton children's height example, what we did is x is the mid-parent height, okay? So we group each mid-parent height with similar or nearby x values, which means that we have a 1 unit interval, like 1 inch interval that we looked at all of the records, okay, with x similarly to the x that we're considering. And then we average the corresponding y values for each group, that is the children's height, okay, that's the observed one, okay? So essentially we're using the predictor to predict the outcome, where the predictor is the mid-parent height, okay, and the outcome is the children's height, okay? So for each x value, the prediction is the average of the y values in its nearby group, okay? And that's what we call it as the nearest neighbor prediction. And so the graph of these predictions is what we call the graph of averages, okay, pretty much what we had done. So let me show you the graph really quick. So this is what we did, okay? So we have the actual child's height, okay, which is all the dots in blue, and the predicted value, which is the nearest neighbor prediction that we did, okay? So again, the x-axis here is the mid-parent, okay? The y-axis is the actual child height, okay? The observed ones and in blue, and then the predicted ones in yellow, okay? So it is, if now put everything into the context of what we're talking about in this topic 24, we talked about association, right? Like correlation between two numerical variable. So if the association between x and y is linear, then the points in this graph of averages tend to fall on a line, okay? And that's a sort of what we have seen, right? Not exactly a straight line, but it's roughly along the line, okay? And the reason again is because when x and y are like highly correlated, meaning that, well, now if we put it back into what we'll be talking about, that correlation coefficient, right? If they have a correlation coefficient, absolute value of that very close to 1, okay? Meaning that the association between this x and y is going to be very linear. Then the points in the graph of averages is going to tend to fall on a straight line, okay? Not exactly straight, but very close to it. So this is just a recap, okay? And I still think it's a good use of time for us to revisit that demo really quick, because later on today, we're gonna use that nearest neighbor prediction as well. So if you go back up to, I guess, back in early March, we've been doing that prediction back then, okay? So this demo is what we did back then, okay? And just to show you what we're doing over here, okay? So this was the starting point. We loaded the Galton data, okay? And then we looked at the father's height, the child's height, and then we used, so by the way, I know some of you are working on similar type of graphs for your project, okay, final project, especially using different coloring. So this, again, will be a good one to refer to if you're trying to do histogram with different groups, okay? So just so you know, because I know some of you are trying to figure out different coloring of your visualization. So this will be a good one. But anyway, so this graph is showing us, okay, we have the father's height, okay, in darker blue, okay, and then the mother's height is in yellow, and then the child's height is the lighter blue, okay? So this is what we observe, okay? So the prediction that we did, just like the nearest neighbor that we talked about, okay, is, remember, we have the father, mothers, and child, so that's the 3 columns, okay? And then we, first of all, okay, just to get a sense, okay, to get the child, just do a child height scatter plot, okay, just to get a sense of how it generally behaves. And then what we did, if you remember, is now we add a parent average, which is what we call the mid-parent height, okay, because that is the one that we're going to use to help us make prediction. Okay, so that's what we're doing. And if we now do a scatter plot of this two, okay, so that's the, sorry, on the x-axis is the mid-parent height, on the y-axis is the child's height. Okay, so we generally see, now we learn about linear, like the correlation, right? So if you look at this graph one more time with the new set of concept that we have learned about correlation, it is indeed showing some kind of positive correlation going on. Okay, maybe not very strong, but at least we can generally see a line sort of like going through it with a positive slope. Okay, so that gives us an indication that these two variables are probably indeed correlated. Okay, and it's probably positively correlated, and then that's an indicator of why you might want to use the mid-parent or parent average as the predictor to predict the child's height. Okay, so now to remember what we did. Okay, so remember we're doing the nearest neighbor prediction. Okay, so what that means is if I'm having the 68 as the parent average, okay, and remember I'm going below 0.5, going above 0.5, so I have 1 inch interval. That is the x value, right? The x is the nearby axis, okay, and we collect all of the records in this between these two bars. Okay, and for prediction for any child's height within this bar, what we do is that we collect all of those records, take their child's height value, take the average, and then that will be the prediction for every record in this range. Okay, so that's what we did. Okay, so remember we are using the where method. Okay, the parent average, that's the column, and then we're collecting between those 1 inch interval. Okay, so this is our actual set, a small set of close to 68 that we're doing this prediction. Okay, and then of course, like I said, you would take the mean, okay, of all of the child's height within this range, and what you get is 67.62. Okay, so that's the predicted value that we're going to use, okay, for any child's height whose mid-parent or parent average is in this range. Okay, all right, so then we do that as a function. And then now we are able to reproduce the plot using the function that we learned before. And this is exactly the plot that we have seen in this slide. Okay, so again, this is one way of prediction. Okay, we call it nearest neighbor prediction. Okay, try to get a sense of why we want to do it in the first place and how it is related to some degree of the correlation that we have talked about. Okay, so again, if the x and y, the relationship or association between them is linear, then the points in the graph of the averages that you're able to do the prediction tend to fall on the line. Okay, and then of course, the stronger the correlation, I think, the closer they're going to be on a straight line that you're seeing. Okay, so for us, overall, this is one way to do prediction. And next, we're going to move to what we call linear regression, okay, which is a more formal way of doing prediction, and then people use that all the time. And I'm sure some of you probably have heard about the term linear regression in the past, and we're going to cover that in detail when we get to the next topic. Okay, so before we move on, any questions about what we talked about here, the nearest neighbor prediction, how does it work in practice, and then whether it makes sense to you and how the code was working on overall? Any comments? Questions? Okay, hopefully this is like freshing, okay, because this was a few months ago, I guess, by now. But with the association and correlation idea, hopefully it starts to make more sense to you. Okay. And before we move on, I just like a overall question to see if anybody has any comments. You see that we call this regression, okay? And many times people are wondering, why do we call regression, okay? I guess in terms of English, if you think about the term. So if we look at this graph, this is the prediction that we're doing, okay? What this is telling us, if you now see here, okay, so for this dot, okay, let's just say for this, let me maybe use the bigger, yeah. So for this dot, okay, this is the child height, right, for a particular record, okay? And that's the observed data, all right? And then for this particular child's height, our predicted value is way below it, okay, in a sense, okay? You might say that, oh, this is not a good prediction. Indeed, I guess every dot that's far away from the yellow predicted value might tell you that for that particular record, the prediction might not be really good, okay? And we keep that in mind because later on, when we learn linear regression, we also need to learn how to make sure that our linear regression model is justified, okay? And those are important things to consider, okay? But if we come back to the term regression itself, okay, I want to draw your attention to like not only this dot, okay, because this dot in particular, you can see that it's above, right, the predicted value, okay? And then when you look at other dots like below this line, obviously below this curve, I would say the yellow curve, then you will see records that are actually the observed value are below the predicted. Okay, so what regression means in this case, especially people also say regression to the mean, okay, the mean average, like the mean value, the average value, is that if you look at this graph, pretty much the prediction in this nearest neighbor prediction and later in linear regression as well is kind of, we are like the predicted value is sort of like regress to the mean. Okay, you're always going to have deviation. Okay, and we've learned about ways to evaluate deviation between distributions and stuff like that. And here, this is a nature, I would say, of doing prediction in this way. Okay, because we're using the nearest neighbor to do the prediction. And when we do the prediction, it was the nearest neighbors. Among all of them, we took the mean. Okay, so there is this effect of regression to the mean. Okay, and that's the main reason why regression is called regression. Okay, and when you're looking at any kind of plots, I mean, in this case, we are having a particular style, I guess, or like the type, the pattern of the dots that we're seeing over here. Okay, and then you might be able to see, like in your project, for example, you might not see something exactly like this one. Okay, you might have other data, like data points that are like more scattered around, or maybe not very clear linear relationships, stuff like that. But regardless, if you were using a regression method like this, you will always see the predicted values kind of regress to the mean. Okay, and so that's why people call it regression in the first place. Okay, so in case any of you are curious about the term, that's the reason. And so that's pretty much for this topic 24. And let me